So today what I'm going to talk to you about is some work in my lab, some fairly recent work on adipose metabolism. I am a metabolic biochemist, so that big chart you see, I actually look at it and I see the big holes in it. And I presume that most of you have fallen asleep in some sort of class that I might have taught, you know. So today I'm going to talk to you about something you probably heard about in the popular press, and it's certainly getting a lot of play lately in the lay press, in the scientific press, and that is brown adipose tissue and the ability for us to all become incredibly thin by activating our brown or beige adipocytes, and that would be wonderful. But let's see what the evidence suggests. So classically, there's been really two types of adipose tissue. The one that I usually think about, and the one that drives me the craziest, is white adipose tissue. So white adipose tissue, you can see on me, and probably yourselves in great excess. And its role is really as a storage organ. So it stores triglyceride for times when we don't have food. So we can lipolyze, we can mobilize that fat and use it in other tissues. And this has been thought to be one of the central components of diabetes. So diabetes is some hypotheses would suggest begin there with a chronic inflammation that's driven by high calorie intake. They don't expend a lot of energy. It's mainly a huge lipid droplet. They just store fat in there, and there's very little cytoplasm or anything else within that cell. Now, in contrast, there's this other type of fat called brown adipose tissue, and we call it brown adipose tissue because it looks brown. And so this tissue has been really had a revolution lately because it's thought that if we could harness this tissue, which does not store fat but burns fat in a futile cycle, that we could just burn fat, we could eat as much as we want, and that we would both be literally and figuratively hot, okay? And so this has garnered a lot of attention through the National Institutes of Health and, like I say, within the press. And, whoops, okay. So we've known for a long time that if you induce thermogenesis, if you make the body utilize energy in a futile cycle, that it is a great weight loss drug, okay? And we've known this since the turn of the 19th century, that we can uncouple respiration. Well, basically, we can make futile cycling occur within an organism, within a human, and we can induce a lot of weight loss. The problem with that is it kills like half the people who take it, and it was one of the first drugs that were outlawed by the Food and Drug Administration. But because we live in modern times and we have the internet, we can get kind of anything over the internet, and we still see patients in the ER that have taken these uncoupling agents, these thermogenic drugs, and this individual just recently, in 2015, died, and if you read the quote, she was burning from the inside. So this is an effective weight loss drug, but it is incompatible with a therapy. But what the thought is if we could harness the natural ability of the body, natural ability of the brown adipose tissue to burn fat, we can eat as many calories as we want, and particularly fat, because it's a fat-burning machine, that we could all be thin. And like I say, this has garnered quite a bit of attention. And we won't go into the biochemistry. If you're really interested in it, I'd be happy to tell you about how this happens. It's a little complicated. Anyway, so we thought, well, there's a lot of circumstantial evidence to suggest that we can do this. So there are circumstances, there are drugs that we know that we use in the clinic that can give you more brown adipose tissue. And in fact, if you do a correlative study, you can find that obese animals have less, lean animals have more. But we wanted to ask the direct question is, if we remove the ability of that adipose tissue to burn fat, do we get obese mice? So we did this genetically, so we were able to generate a mouse where we can, in a cell-specific fashion, remove the ability to burn fat. And so we did this in adipose tissue. So we have mice that in their adipose tissue cannot burn fat. And so the expectation then is that they would not be able to regulate their body temperature and they would be obese. So in fact, when we did this, we got mice that were cold intolerant. Their normal temperature at 21 degrees or at room temperature, but then when we put them in the refrigerator, or let's say we model them going out on a cold day, control mice can do this very well. So if we look at their core body temperature, we put a normal mouse in the refrigerator, then they're able to maintain body temperature. Their core body temperature stays the same. Okay? No matter where you go, mainly your core body temperature stays within a very tight range. But these mice, they drop like a rock. And in fact, we have to remove them from the experiment or it would be lethal. Okay? So it is absolutely required in an autonomous manner for thermogenesis. And you can see the control brown adipose tissue is brown. But when we remove the ability of it to burn fat, it becomes this milky white color. And because it's packed with lipid. It's packed with fatty acids because it can't burn them. So now the expectation is we've removed this ability of adipose tissue to burn fat, that we would get obese mice. Okay? So we put them on low-fat and high-fat diets, and it's irrelevant. It's irrelevant at 21 degrees that we've lost this ability to burn fat in adipose tissue. All right, so that probably doesn't make me particularly popular, but I just have to, I mean, this is not a hard experiment. It takes gravity and time, but there does not seem to be, at least in our hands, a large component at room temperature. Okay, and in fact, the mice are not less diabetic. They don't seem to have any of the any improvement in some of the comorbidities that are associated with increased weight gain. So this is actually reminiscent of something that we had known for quite some time. So so years ago, researchers have removed the ability of this brown adipose tissue to burn fat in other ways and more systemically. But what they ended up finding was they get a very similar phenotype. They put the mice on a high-fat diet, and they don't see much of an improvement in weight gain. And so it really killed the field for a long time. It really diminished the enthusiasm until another paper, actually several kind of independent things happened. One is that we had kind of thought of humans as only having brown adipose tissue when they're born. So there's an interscapular area that newborns have, particularly to keep them warm, okay? But as adults, we've somewhat lost this ability. But it had been rediscovered in adult humans that there's a small amount of brown adipose tissue in your core. And the thought is that if we can modulate that and improve upon that, improve upon how much there is, that this could improve body weight regulation. But the other thing that came out was that, well, maybe we're doing all of our experiments wrong. And the wrongness of it is that mice don't have clothes on, but we do, okay? So we don't go to the animal room without clothes on, and in fact, no one wants to see that. But if you then take these mice and put them at the temperature that they want to be at, which is 30 degrees Celsius, then they can start revealing some of these phenotypes. And now you can get these same mice that are whole body knockouts of thermogenic proteins to now gain weight. And they gain an enormous amount of weight, and maybe this is more closely matched to humans. And in fact, there's a lot of interesting physiology that happens when we house mice at different temperatures. And so if we just look at UCP1, which is a thermogenic protein, which is it regulates the amount of heat that brown adipose can make, it's regulated by temperature. So if you put the mice a little bit of cold, a little bit of hot, its expression changes. And what's interesting, there's a lot of interesting physiology that goes on because the inside of the mouse, of course, stays the same temperature, but they have to react to their outside environment. So when they're cold, when they're mildly cold stressed at our normal working room temperature, they have to eat more food and they have to expend more energy because they have to maintain their body temperature. And in fact, there's a whole host of interesting physiology that's going on, even so much as when mice are housed at thermal neutrality, they can get rid of tumors much easier. So it's actually kind of driven some thought that maybe being in a hot tub might be good for, well, a lot of things, but including cancer therapy. So what we had, again, been kind of forced to ask is, well, if we put these mice at different temperatures so they can't burn fat in an autonomous manner, are they able to now become obese? So we were able to monitor their energy expenditure over time, and again, this is really interesting physiology. So if you're at 30 degrees, their energy expenditure is quite low, and of course you can see the up and down of energy expenditure because the mice are more active at night. And then when we change the temperature acutely, you get a huge spike in energy expenditure, and another huge increase in energy expenditure upon even going a little bit lower. However, even though these mice are thermogenically incompetent in brown adipose tissue, these types of changes, they're able to adapt quite normally. Okay. So, but what was also interesting was we put these mice at thermoneutrality and fed them a high-fat diet. And the first thing we saw was we couldn't find any brown adipose tissue in them anymore. So by putting our knockouts, the ones that cannot oxidize fatty acids, can't burn fatty acids in adipose tissue, they completely eliminate brown adipose tissue. It's actually quite amazing. My graduate student has dissected thousands of these mice. I probably shouldn't say that. Anyway, and she can't find it. She knows what she's doing, and it's just not there. Even histologically, it's hard to find. So now the expectation is, now we have mice that have it, and we have mice that do not have this tissue, this thermogenic tissue, that now they're going to be obese. And they're not. So we don't find any evidence that in an autonomous manner that we can burn our fat away, or at least from a not from a therapeutic standpoint, but from a basic science standpoint. So this is somewhat against, I think, the very, very strong push that the field is putting on as to whether brown adipose tissue is really playing a role in regulating our body weight. And in fact, these mice are not more diabetic. They really are very similar to their litter mates. And so I just want to leave you with, well, we really have not found a lot of evidence to suggest that this is going to be a viable therapeutic target. It's obviously very important for cold-induced thermogenesis. Mice cannot survive in the cold without it. But we don't see a change in body temperature at any ambient temperature. It's just a remarkable metabolic and physiological adaptation where the mice are able to maintain normal body weight even though they can't do this very highly energetic process. And so one of the things that we really like to ask is, well, this is really, does brown adipose tissue play a role in obesity? But can we use it now as a therapy? So we know a couple of ways that we can modify how much brown adipose tissue a mouse has. And so here, what the other remarkable thing that I didn't have time to tell you about is that in our mice that can't burn fat in their adipose tissue, they also can't make new brown fat. Their brown fat it doesn't work normally anyway, but then we can't induce more of it. So it's a really great model, I think, moving forward, is that we can take a control mouse and we can take most of their subcutaneous adipose tissue, white adipose tissue, and turn it into this brown, thermogenic adipose tissue in several different ways. These are not proprietary drugs. We know how these work. But our mice do not do this process. So now what we want to ask is there a real therapeutic potential, or are we barking up the wrong tree? And that's what I'll leave you with today, because we're just starting those experiments. So thank you.